Hello my dear students, Assalamu alaikum. This is the lecture 3 of gravity and gravitation. Today we will discuss about escape velocity. So now what is escape velocity? The minimum velocity with which an object is thrown from the surface of any planet and it does not return to the Earth's surface, at which velocity the object is thrown and it just crossed the gravitational field and it does not return to the Earth's surface. So that this velocity is called escape velocity. If we throw an object with a velocity, escape velocity, and this object does not return to the Earth's surface, it goes from the outside, it goes outside the gravitational field. This velocity is called escape velocity. Now we will derive the equation of escape velocity. Look at the picture. This is the Earth. Total mass of the Earth is located at the center of the Earth. Total mass of the Earth is capital M. When an object of mass small m is thrown from the surface of the Earth with a velocity be means escape velocity, and this object just crossed the gravitational field. So assume now this is the gravitational field of the Earth. Gravitational field of the Earth is extended from surface to the infinite distance. Gravitational field of Earth is extended from the surface to infinite distance. So this is the infinite distance, small r equal infinite. At this point, small r equal radius of the Earth, cos this is the radius. When the object is located at the surface of the Earth, at this point small r equal radius of the Earth. This is the radius. Now at this point the kinetic energy is half mbe square. When the object just crossed the gravitational field, of Earth, at this point the velocity will be 0, so the kinetic energy is 0. At this point the kinetic energy is 0. So the change in kinetic energy when the object moves from the Earth's surface to outside the gravitational field, the change in kinetic energy is del ek is equal half mbe square. So this is the change in kinetic energy, and this is the equation number 1. When the object moves from Earth's surface to the outside of gravitational field, in this case the total work done from Earth's surface to outside the gravitational field. From work energy theorem, the total work done is equal to the change in kinetic energy. So now we'll calculate the work done from Earth's surface to outside the gravitational field when the object moves from Earth's surface to outside the gravitational field. Now we will consider the point A and B, a small displacement dr and small displacement dr when the object moves from A to B. Small displacement dr, in this case at the point A, the gravitational attraction force between object, when the object reach at the point A, mass of the object is small m, and the distance from the center of the earth to the point A is small r. So the force is F equal G capital M small m divided by small r square. When the object moves from A to B, in this case displacement will be small. For this reason, force, the gravitational attraction force, nearly equal between these two, nearly equal when the object moves from A to B, cause dr is too much small. Now the work done when the object moves from A to B, the work done, small work done, in this case small work done dw equal F dr. F dr is the small work done. So F equal G capital M small m divided by r square dr. So now we will calculate the total work done from Earth's surface to outside the gravitational field. Now integrating this equation from surface to the infinite distance, surface to the outside of the gravitational field. So total work done, integrating this equation, integration dw equal integration G capital M small m divided by r square dr. So the limit is small r equal capital R to small r equal infinite, cause object moves from surface to the outside of the gravitational field. Now integration dw equal integration small r equal capital R to small r equal infinite G capital M small m divided by r square dr. So capital G is the gravitational constant, capital M is the mass of the earth, small m also the mass of the object. So this capital G capital M small m are constant, and now integration dw is equal w total work done, and G capital M small m is constant, and taking outside the integration. Now integration r square 1 by r square means to the power minus 2 dr, small r equal capital R to small r equal infinite. So now G capital M small m integration r to the power minus 2 dr is r to the power minus 2 plus 1 divided by minus 2 plus 1, and this is the third bracket, and the lower limit small r equal capital R, and the upper limit small r equal infinite. Now minus 2 plus 1 is minus 1, this minus sign taking outside the third bracket. So w equal minus G capital M small m, and r to the power minus 2 plus 1, that means r to the power minus 1. So we will write r to the power minus 1 means 1 by r. So the limit is small r equal capital R to small r equal infinite. Now w equal minus G capital M small m minus G capital M small m capital M small m, and one small, these are replaced by infinite, cause higher limit infinite, so 1 by infinite minus 1 by capital R. So 1 by infinite means 0, and this minus sign and this minus sign plus. So what done? W equal G capital M small m divided by R. So this is the work done. So from work energy theorem, work done is G capital M small m by R, and the change in kinetic energy is del Ek is half mb square. From work energy theorem, change in kinetic energy is equal to work done. So half mbe square is equal to G capital M small m divided by R. So escape velocity BE equal 2gm divided by R. So this is the formula of escape velocity. Here small m cancel from both sides, and 2 is multiplied by gm, so 2gm by R. So square root from both sides, then we get escape velocity BE equal root over 2 capital G capital M divided by R. Now another formula of escape velocity, we know that the gravitational acceleration at the Earth's surface small g equal G capital M divided by R square. Now G R square equal G capital M. So put the value of G capital M in this equation. Then we get BE equal 2G capital M means GR square divided by GR. Now 1 R capital R upper and lower part, capital R is cancelled. Now we get escape velocity BE equal root 2GR. So this is the another formula of escape velocity. G is the gravitational acceleration at the surface of the Earth. R will be the radius of the Earth. So this is the constant. This is a constant quantity. Put the value of gravitational acceleration and the radius of the Earth. Then we get the escape velocity for Earth is 11.2 kilometer per second. 11.2 kilometer per second. Now escape velocity is different for different planet, but for a fixed planet escape velocity will be constant. Escape velocity must be constant for every planet. Now we solve a creative question, Dinaspur board 2019. Here the question, name of the planet Mars and Earth, mass, radius. This is the question. Question C, determine the acceleration due to gravity on the surface of the moon, of the surface of the Mars. On the surface of the Mars. We know that the gravitational acceleration at the surface of the Mars is Gm is capital G capital M divided by Rm square. Here mm is the mass of the Mars planet and Rm will be the radius of the Mars planet. Put the value of mass of the Mars planet and radius of the Mars planet, then we get the gravitational acceleration on the surface of the Mars planet by using this formula. And question D is, will the escape velocity of the body for both planets be same or not? The formula of escape velocity is BE equal root over 2 G capital ME by RE square. This is the formula for Earth. Here M is the mass of the Earth and RE will be the radius of the Earth. Similarly, we will calculate the escape velocity for Mars planet. Here mm is the mass of the Mars planet and Rm will be the radius of the Mars planet. So using these two formula, we will calculate the escape velocity for the planet Mars and Earth. Then we decide in which planet the escape velocity will be greater or smaller or same or not. Okay, thanks to everyone.